Good morning everyone, welcome to Data Structures course. Today we will first discuss about dynamic array allocation and static array allocation. In dynamic memory allocation, whenever memory is allocated, the memory size can be changed. This allows reusing the memory. The user can allocate more memory whenever required, and user can also release this memory whenever the user needs more memory. So this doesn't happen in static memory allocation. The memory remains allocated from start to the end of the program, and the user cannot reuse the unused memory. In static memory allocation, the memory size cannot be changed. If we look at the syntax of dynamic array allocation and static array allocation, we can see that in dynamic memory allocation, we have a pointer pointing to a whole array, and we can also free up the memory whenever required. This syntax is for C++, and this memory representation shows us how a pointer points to an array which is dynamically allocated inside a heap. So that is why dynamic array allocation is more beneficial. Now let's talk about advantages of linked list over dynamic arrays. In case of linked list, the insertion and deletion is a constant time operation, and in the case of dynamic arrays, if we have to delete an element present in middle, let's say for example this element, I will have to allocate a new array and copy the first half of elements into the new array and also the second half of elements in the new array. This will increase the time complexity, and thus linked lists are better in this case, as we can insert and delete in constant time. Now in the case of linked list, the memory utilization is also better because we can use fragmented memory, while in the case of dynamic array we need memory right next to each other. So these are the advantages of linked list over dynamic arrays. So why recursion is useful? Recursion is an amazing technique which can be used to reduce the length of our code and make it easier to read and write. Recursive function can also be used to solve tasks in elegant ways, because recursion breaks the problem into less complex steps and comes up with easier version of solution. So the smaller code and easy to understand are the two main reasons why it is useful. Now let's look at an example of recursion. Factorial. We can represent factorial of a number n using this mathematical definition, where f of n is representing factorial, and it can be broken down as n into f of n minus 1 for all n greater than 1 and 1 for all n less than or equal to 1. Now this mathematical definition can be converted to code using recursion by simple code as shown here. This is the base case of recursion, where our recursive function terminates and each time f of n calls f of n minus 1 into n. So this is how elegant a recursive code is. So now let's talk about why tail recursive functions are better than general recursive function. The main difference between traditional recursion and tail recursion is when the actual calculation takes place. In traditional recursion, the calculation will happen after the recursion call, while in tail recursion, the calculation occurs before the recursive call. Hence, there is no need to maintain the intermediate variables before the tail recursion moves to the next recursive call. Let's understand this by an example. Previously, we saw for factorial function a normal recursive function, and now if we look at the tail recursive version of this factorial, we will see that we have a wrapper function fact which calls fact tail, which is a tail recursive function, and it doesn't do any calculation after the last recursive step. So there is no need to maintain a stack for storing the variables, hence it is optimized and it's a better version for recursive functions.